basic definitions to be acquainted with this vertical dynamics. Those are nothing but vibration definitions. So we have a definition of ride for sprung mass vibration, definition of shake for sprung mass vibration, and harshness and boom, and then followed by unsprung mass vibration, that is wheel vibration and axle vibration, and then steering system vibration. So these all definitions we are supposed to be very much familiar. So when you take tire noise and vibration, you have the definition of tread noise, sizzle, and so on. So these all are stacked as an appendix in popular textbook, Fundamentals of Vehicle Dynamics, Gillespie. I've just had a screenshot of them, what is necessary for this part. So you have for the entire vehicle dynamics, the important definitions. Please go through the chapter 7 of Gillespie. And after going through these all important definitions pertaining to vertical dynamics, we have looked at this all vertical dynamics is study of vehicle as a vibration model. So the vibration model is been excited by an important source, broadly classified as two sources. One is surface irregularities, another one is onboard sources. So surface irregularity is that measure of roughness of the road. And onboard sources are aerodynamic forces, or it comes from engine, or it comes from tire wheel assembly. Any rotating bodies in the vehicle, all are the sources for, again, vibration of this vehicle. So these all can be perceived by occupant by these three paths. It can be a straight contact path, tactile path, or through the visual contacts, or by oral path. That is auditory sensation. So looking at this excitation sources, we have defined what is the main objective of the ride dynamics. It is to make a control strategy so that passengers' perseverance of comfort is good. That means discomfort level should not cross any the defined level, certain boundaries. So in order to meet that objective, we need to understand, we need to have a fundamental idea about human response to vibration and the vibration behavior of vehicle and characteristic of road surfaces, irregularities. So with that, we have marched ahead of looking at one by one. So when you look at the human response to vibration, it is a highly complex phenomena to predict because of the nature of subjective way of perceiving. Comfort for one is not necessarily comfort for the other. So in such case,
Hello.
Yeah. I hope you are able to see the screen again. So we were looking at this human response to vibration. One of the fundamental importance of understanding, or go ahead with this vertical dynamics. So it is very complex to have quantitative measure of this human response for the vibrating vehicle. So that can be traditionally done by subjective ride measurements. So, you know, we had a detailed discussion in yesterday's class that the subjective measurements can be done by an expert jury to comment on ride comfort or quality with the various class of vehicles on different operating conditions and so on. But however, that cannot give you the quantitative assessment to define those boundaries or some numbers that can talk on whether passenger perception of vibration is in allowable limit or not in allowable limit and so on. So for that, there are many researches, many research data are available. They have been conducted in the laboratory and on the road condition. This we have discussed in the last class. And then we had come out with looking at some important boundaries, ride comfort criteria given by SAE based on these type of laboratory and on-road tests. So this particular SAE J6A, Ride and Vibration Data Manual, this Janeves criteria defines the amplitude level, the boundary of amplitude level permitted from 1 hertz to 60 hertz, distinguished by 3 ranges, where you can see this amplitude drops as a function of frequency. You see, as an increasing order of frequency, the amplitude permissible or experienced by the occupant is lowering. For example, at 40 hertz, you should have a low amplitude of vibration as a boundary condition. So if the vibration felt at this is felt at 40 is so severe. So that is what is that you understand from this. And these 3 zones are categorized based on jerk, acceleration and velocity. So these amplitudes can be obtained from these maximum values of these 3 parameters. So this is what also we have seen in the last class. Like SAE, Janeve's recommendation, there are also some other standards to express the comfort boundaries for the occupants. So one such criteria is whole body vibration proposed by ISO 2631. So again, this all are from the ride measurement test on the fields. So they had the frequency range consideration from 1 to 80 hertz to have 3 distinguished ranges. So one is called an exposure limits, primarily for the purpose of preservation of the safety of the vehicle. The second criteria is fatigue or decreased proficiency boundaries, which are again for preservation of working efficiency. So what do you mean by working efficiency? A driver has to comfortably drive the vehicle without any problem for a prolonged time. He will not be under any fatigue. So the boundary is what is defined by this. If you see that, again, the third criterion called reduced comfort boundaries, which are again consideration of preservation of comfort. So out of these 3, what would you think will have higher amplitude boundary limits? Is it the first case or is it the third case? Can anyone?
Third.
Third case. You mean to say the higher value of amplitude is permissible for reduced comfort boundaries? No. Reduced comfort boundaries are achieved, the amplitude of vibration felt should be very less. The limits are very less. That you can just see from the following slides. So look at here the human response to vibration of the whole body vibration in vertical direction as well as in transverse direction. So this B graph is for lateral direction as well as for the longitudinal direction. And this A graph is for vertical direction. So if you look at these graphs, that graphs on vertical axis are acceleration, RMS values. As function of frequency, it is given. And if you look at, there is a value of frequency till this frequency range, the amplitude keeps dropping as function of frequency. Then it's stable. Then again, if you see that amplitude can be permissible for these higher frequencies. So what I mean by that is vertical vibration amplitude of 20 hertz, suppose it can have a boundary value for 8-hour exposure or 8-hour of test is done. This is a permissible amplitude. Whereas if you go for 10 hertz excitation to the vehicle, you will have the permissible amplitude is this. So this is the range for from here, this 5 to 10 hertz. So you have stable amplitude appears there. So another important aspect here is, as you are increasing the exposure time during the test of the subject here is the occupant in the vehicle. So if you see that exposure time increases, the amplitude boundary also decreases. That is important understanding on this. So it is also intuitively, or you feel that is correct, that the more the time you are in a vibration environment, you will have your averaged amplitude of that should be lesser value. That's one thing. So the same way you can look at this. And this graph is for the fatigue and decreased proficiency limits. So fatigue and decreased proficiency limits means what? A driver could comfortably drive the vehicle. Reduced, see, we look at again here if you see, reduced comfort boundaries refer to a normal functioning inside. So when you are traveling, you are able to read, write, or eating in the vehicle without any problem, then you'll have your amplitude of vibration lower value. When you the safety point of view means you are not much worried about comfort. That means the safety to be preserved, the exposure limit, the amplitude can be more. So your vibration amplitudes are higher, it's a safe vehicle, but it is not a comfort vehicle. So always you see that standards are given, the test data are presented in the data ISO 2631 for this fatigue or decreased proficiency boundaries. And if you look at the boundaries for exposure limit, that will be of 2 order higher than what is there for this. And for the reduced comfort boundaries, the amplitudes on y-axis, what you see, can be 3.15 times lower than what is there for this fatigue or decreased proficiency boundaries. So what is that you see in this slide is for the second criterion of fatigue or decreased proficiency in vertical as well as in transverse and longitudinal direction. So if you see here, this is what is 10 dB level. So whatever that you have here, say for example, 8 hours exposure time boundary lines are given by this, and that will be reduced by 10 dB level, all the values for the comfort criteria. That will be increased by 6 dB level for exposure limits, this criteria. So that is simple that this dB here written is simple. You have a reference acceleration. So whatever the acceleration by 1, log of that multiplied by 20 is what is 2 dB. If the ratio is 2 order, log of 2 multiplied by 20 is what is 6 dB. If the ratio is 3.15, log of 3.15, natural log of 3.15 multiplied by 20 is what is 10 dB. So the 10 dB less in this values for the third criteria, comfort criteria. Exposure criteria for safety to preserve, you need to have 6 dB more than what is this existing. So these are all something, an understanding of looking at this human response vibration boundary limits. Because after all, you are working in an industry later and you are doing your vehicle testing and you are going to calculate your amplitude of acceleration by employing necessary sensors called seat pad accelerometer sensors. And then you are looking at this RMS acceleration pursued by a human contact. And then you do the test for a number of hours. Or you do some test in the test track for some 25 minutes. Then you should get your values so that it will be a safer vehicle. So you will be able to assess. So as a test engineer, you are working, you will have in your hand this ISO 2631, and there are such many standards, more are there. Here in particular for discussion, I have shown you this sample, and you should be familiar with these all standards. And then you will test your vehicle whether are they meeting the expected level of vibration to express the quality of the vehicle. So marching ahead, you look at here, this is what I just...
Excuse me, sir.
Yeah. Yeah, please.
So what exposure time, what does it actually mean, sir?
Exposure time, see, for example, we have looked at here, these are the tests, right? So for example, I have this shake table test, right? So shake table test, I am using it to find whole body vibration phenomena. That means a rigid seat will be there where the subject, the driver will be sit on that, and you will be exciting that seat with the individual harmonic frequencies. With the individual harmonic frequencies. For example, you will excite 1 hertz for some time. And that excitation table will be there for how long is what is this exposure time. If it is for 1 minute, and then you are having your average value of that for that particular frequency mark. Then for the next, you will increase one frequency, then again you will have it. Next, you will increase the frequency, then you will have it. Like that, if you mark, you will be able to plot such graphs. So it's a fit of the data. So this exposure time here, is the subject, how long is under the vibration bench or vibration test way. Is that clear, Srisha?
Okay, sir.
So going ahead with this, no, so again you can look at here the same graph, RMS acceleration in 1/3 octave band. So, 1/3 octave band is to compress the range of frequencies to put it precisely. So you'll see what is this all later on. It is the frequency ratio power 1/3. In particularly in noise, when we are dealing with, we will be familiar with these terms. So instead of having 1-2 frequency like that, you have here the 1/3 octave band frequencies and the amplitude. And this is taken from this previous graph only specifically, right? So that is what is for a specific one particular vehicle which is of 80 kilometers per hour on a smooth road test is done. So this is ride measurement criteria. So if you look at these, all dots are below this. So that means these measurements are confirming the vehicle comfort quality, right? So this again for this reduced comfort boundaries, this has to be these values, these boundaries will come 10 decibel below, dB level below. That's what is this graph. And then going ahead with that is look at now, after all this, after understanding human responses from the vibration of the vehicle, now how do you quantify this vibration? So the quality of your measurements are quantitative terms. How do you find the RMS acceleration value, and we are able to correlate that to the subjective evaluation, which is the traditional method. But that is not sufficient. So still you have to march ahead for an engineering analysis to improve the quality of your vehicle. So when you have to look at quality of your vehicle, for that matter, any system, mechanical system quality, you should be having on hand the nature of its vibration. That primarily says that what are the natural frequencies, what are the normal modes of vibration, what is the damping present in the system, and so on. So these all data are important for the system. So if that is for the vehicle, how do you get those values for the vehicle? So you need to make your vehicle as a vibration model. So how do you make your vehicle as a vibration model? You should make your vehicle as a combination of lumped mass and spring system. So one such model is there in this slide to represent an entire vehicle, right? So you know this is sprung mass and these are unsprung mass. You know what is sprung mass and unsprung mass. And this 7.3 figure represents 7-degree freedom ride model of a passenger car, wherein the front axle is independent. So independent suspension, rear is solid axle suspension. So you will have here these two unsprung mass bounce, and you'll have this axle bounce as well as roll, right? It's getting, time is getting up, so roll. So you see this models here 2 degrees of freedom, here 2 degrees of freedom, and the sprung mass as 3 degrees of freedom is vertical oscillatory motion, and angular oscillatory motion about y-axis and about x-axis defines pitch and roll. So these 7-degree freedom model. The same thing is this picture is taken from Jasser textbook. You can also have instead of this all 4 wheels of independent suspension, then you'll have 4 bounces and 3 sprung mass degrees of freedom, right? So now how do you get from these models your natural frequencies, mode shape, and so on? For that you need to get your fundamental governing dynamic equation of this vibration model. So that can be obtained by Newton-Euler equation. When you have like this coupled translation and rotation and this all there, or you can also get by applying Lagrange equation with the dissipation model. So that is a popular one, where Lagrangian is called as the difference between potential energy, kinetic energy, and potential energy. And you have that set of Lagrange equation which you have studied in your fundamental vibration course, or you can refer to Jasser textbook. You have Lagrange equation applied to derive the governing equation. Once you have the governing equation derived, you will be able to solve those equations to get your vehicle response, or to solve that equation considering free vibration model, making that governing equation as a homogeneous equation. You can find your natural frequencies and the amplitude ratios for the mode shapes. So that is that known fundamental approach of vibration problem solving. So this is one such a model. So if you look at, if you have more degrees of freedom in this, if I have an occupant also considered to be a lumped mass, and then their contact with seat, I can keep increasing this model from 7 degrees, more and more degrees of freedom complex models, to have precisely my engineering analysis to do to improve my vehicle. But that solving them, getting the equation, solving them manually is difficult. That's where you see an advantage of computers, right? So you can see that later. So now coming back to that, it is not necessarily that all the time you should have a complex.
So,
yeah. Yes, Pranav.
so that 7 DOF you are saying, no, like can you can you say me like what where the degree of freedom in
What
front
are those?
axle the yeah
Yeah, look at in this, you have this front tire wheel assembly. So unsprung mass essentially tire wheel assembly and the connected members to that. So if I consider this is sprung mass, 2 sprung mass in the front, it will have a vertical oscillation motion. So here one and here one, and here it is connected by the axle. So this together will bounce, or it will have your roll motion. The roll motion is what we call it as a, what is that? A tramp. So it can be parallel tramp or opposite reverse tramp. We have seen, right? So that there are 2 degrees of freedom. One is this bounce of this axle and roll of this axle. So, and then sprung mass can have its motion in vertical direction, translational oscillation, and it can also have an oscillation, angular oscillation about y-axis called pitch, about x-axis called roll. So these all 3 for the sprung mass and 4 from the unsprung mass constitute 7 degree freedom model.
okay, so this is this ride model is like a default 7 degree DOF. And you are also saying
yeah,
like
this is the minimum degrees of freedom requirement model for a full car. I can go up to 54 degrees of freedom for that vehicle. So I have inside occupants, their seats. So if I see all the occupants are another 4 masses, so their degrees. So like that, I can have the degrees of freedom from 7 keeps increasing to describe the whole model with the subjects inside. Subject me here is the occupants, driver occupants all. So the model can be further and further made more complex. So you need a computer application to solve, which people are doing it. There are theses where people have made up to 54 degrees of freedom model to understand what is actually coming. So these models are the alternatives for the laboratory test. You do not really require a laboratory 4-post and then you put the vehicle and put the dummies inside with instruments sorry, which are representing the humans and so on. So this is a complementary approach analytically to look at to get your right parameters of the vehicle, which are essentially natural frequencies, amplitude ratios, and the damping or the phase information between the vibrating lump masses. Right? Yeah. So
sir, another one more doubt.
Yeah.
Like you hello?
Yeah.
Hello?
Yeah.
Sir, like you were saying like it's a lumped mass, and before like starting this default 7 DOF itself, we are considering as a lumped mass.
Yeah.
And for one like whole car, lumped mass in a sense like it's a total quantity of subject, right?
No, lumped masses now, see in this model, how many lumped masses are there? 1, 2, 3, 4.
Okay.
Correct. So the entire mass of the vehicle is total mass or weight of the vehicle is now discretized as sprung mass, as unsprung mass of left hand side front wheel, right wheel, like that. So 1, 2, 3, 4. These are 4 lump masses connected by springs and dampers to regulate your model with the
Understood.
elasticity, right? Yeah.
Yes, understood.
Yeah. So we do not require necessarily for some qualitative assessment of your vehicle ride, not a very big, huge, complex degree of freedom model. Because there are some important motions like bounce and pitch, roll, only when they are important as a whole of your sprung mass. If you know that is the sprung mass critical resonant frequencies, And those data are sufficient to design your suspension in order to have the amplitude of those vibrations. You cannot get away from those vibrations, but those vibrations should have a limited amplitude of vibration, so that whether you look at say your criteria of comfort from Janeway's criteria or ISO 2631, those values are well within the boundaries of amplitudes. So that is the interest. So for such study, the simplified models like the following: a quarter car model, 1/4 of the mass, sprung mass over one wheel. If I consider the road undulation excitation can make this model to vibrate, right? So I can come to know what is the natural frequency of sprung mass and unsprung mass. Essentially, this is bounce frequency, and this is called a half frequency, wheel half frequency. So these frequencies values, and then the amplitude ratios of them can also sufficient to have an insight of to talk on an important motion called the bounce. And if you want to improvise, you can also see there is a model of quarter car with the human attached here. The equation, governing equation, and getting natural frequencies all are available in JASA textbook for your reference. And continuing with that, look at another model called the pitch and bounce model. So your entire vehicle has been made here. That the mass of unsprung mass is not considered as compared to the mass of this, and the spring and tire spring stiffness are combined equivalent. We will see these models in detail in coming classes, but this is a model where it couples your bounce and pitch motion together. So there are important design aspects of springs to look at these natural frequencies, which we are going to discuss. So this is again from JASER. Whatever is there in this color diagrams, all taken from JASER, which are equivalent picture. And similarly, if you continue with that bounce and roll model, so again it's a half car model. You have this unsprung mass and your sprung mass. So these two bounces, and this now going to have bounce as well as roll. So you have a governing equation for that to have a similar way to get these parameters. So these all models will be quite sufficient to design your suspension. This data is going to help you to design your suspension, right? And these data can be, this model can be excited by a regular sinusoidal excitation, and you can look at it. See, I know this sprung mass frequency is near 1 Hertz for the roll. I will excite this so that one bounce and rebound like that. Then I can make this roll. So when I make this roll, what is the amplitude of vibration is the measure is going to tune my suspension design. So that is how we can work on design of suspension.